Okay, so we start today's lecture. I have to apologize about the two previous ones that were skipped without proper information about it. The first one just happened to be before the holiday, when the institute didn't work, and the previous one was skipped just because there were no participants. Now maybe somebody is going to return, so we start. Anyhow, we are in the middle of the course, and it is the course devoted to Grotendika topology, and it is high time to give at least a preliminary definition. So this is going to be preliminary, and I'm going to give it compared with the classical topology. So the topology can be classical, or can be Grothendika. In the first lectures we have considered for a topological space X, in fact, two categories. That was the category of open sets. How did we denote it? Perhaps like this open X. It was small, a small category of open sets where the morphisms were defined like in any other partially ordered set. And there was, what was defined was the category of coverings of X that was considered in two versions, either small in a more classical sense, or classically, or arbitrary. The objects of which were the pairs I, like I and U. That was the mapping from I to this set. As this was the difference of in the usual form is considered just as a set of open subsets of the topological space X, and I was an arbitrary set. That's why the category is was supposed to be arbitrary, not even essentially small, even if we consider only compact spaces and finite coverings. And there was one more element of the category approach to topological spaces. There, so the category open X was small, but with the only final object that is is of course X itself. So this was the list of objects for the classical topology. And as for the Grathendik one, there is no such thing as the topological space, set the main object is the category of coverings, and in the most generality it is arbitrary. Well, and well, in the interesting case, or rather sometimes no final objects, and this is the main difference. No final object. This is the main difference between the classical topology and the Grathendik one, and the main feature of the Grathendik topology theory that places us beyond the set theoretical foundations. So we are not working with general Grathendik topologies. We don't work with a set and its subsets, or geometrically speaking, there is no such set inside which all the geometry happens. Perhaps I try to reflect it with a very symbolic picture. If here is X, then there are open sets, and in the Grathendik case there is something maybe mysterious, but when we are going to work with the special Grathendik topologies, there will be some analogs of the open spaces that are going to be also called opens, and they are true set theoretical mappings, but no more the inclusions into any, sorry, perhaps I've drawn it differently. It's not a set, it is something more general. So at the very beginning, the traditional topological images should be switched off, but not completely, because the best point of view to understand Grathendik topology is to see them as the very natural generalizations of the classical topological objects. And the main goal of today's lecture, which just continues the one that was before this, in terms of the motivation of such a consideration in just one class of important cases. So these were the introductory remarks. In fact, the full set of axioms is rather long, so the definition is preliminary. There are the classical books notes by Artin, Mumford are the real daters. Of course, the Grathendik himself contributed a lot to this theory, but he did not write anything exactly foundational. And there are lots of other materials, but this was just, in these texts we can find the beginnings of the theory, well, axiomatized in a very important and clear way, in which it can be perhaps compared with the Euclidean's foundations. Well, I recommend to look these texts through, though of course the formal definition will be presented here after we have the one classical example that we discussed today. Any questions about this part of our lecture? Okay, so I erase everything and
so no final object means like for some spaces there are no kind of algebraic universal cover, right?
Well, it's a good analogy, the universal covering, but I would say for a rather special kind of topologies, like the topologies of the sets with the action of a group. But I think that the concept of universal covering is, however, rather special. And well, in the case we are going to discuss today, it has to be taken into account, but not quite literally. We'll return to this important question in a while. So our main motivation was the concept of the moduli spaces, and there are two standard words related to them. The coarse one, so as usually we fix the ground field that is, as usual, supposed to be algebraically closed, and there are moduli spaces that we denote M sub j of k. Yes, j is just a natural number. The genus of the curve, and this is called a coarse moduli space. These any of them is called a coarse one, and I'll perhaps make a comment about it. It is for every set, every j, it is the, for every j, it is the set with several structures. Several structures. Well, in terms of algebraic geometry, the main ones are the structure of quasi-projective varieties. And well, I would say maybe in an approximately way, it took about 100 years to define this structure of quasi-projective varieties. Well, I should restrict my writing. Yes.
Yeah.
Does it work?
Yeah.
So, for a long time it was studied using other structures that are going to be also mentioned. But what is much more important, and here I have some problems in writing the appropriate font, G over K, that it is a fine modular space, and it is not what is most important, that is, it is not a set. It is, I would say, it doesn't differ from a set in any crucial way. However, it is not, and it is one of the main and very important and very convenient examples of Grothendieck topology. Among other things, using what is now written on the blackboard, I should mention that this 100 years is not a random difficulty, mathematical difficulty that was overcome for such a long time. The thing is that the natural existence of quasi-projective manifold is to be defined by equations in some projective space. And it turns out that this is the most nasty and wrong way to work with moduli spaces. The best mathematicians understood it step by step, because, well, for genera like below 10 or something like that, it is theoretically possible to look at moduli spaces, coarse moduli spaces, as at the usual quasi-projective moduli. Then it becomes harder and harder, and finally it turned out in, maybe I write it down, that about 90, I think 80 something, there was a great theorem of Harris and Mumford, who realized that while the genus grows, the MJs become quite counterintuitive. Maybe I say a few words. In what sense it is so? Well, in the world of things are with ample anti-canonical class, like for curves and surfaces. These are the curves and surfaces of general type, and well, the rational types are close to them. While this Nj with the genus starting from about 25, it turns out that formally the modular spaces are of general type. Well, this is the precise equivalent, precise statement that was a sensation in 80s, because in my student times, in 70s, it was widely believed that all these spaces are are unirational. That means that the universal family of all the curves of given genus can be written down. Well, better to call it versal, not just universal. And we'll soon consider it by the examples. And well, Severi, one of the classics of the subject, really believed in it. And then there was a counterexample. It is starting from the genus 25, they are of the coarse moduli spaces are general types. However, as we see immediately, they have lots of rational subvarieties. It is not at all so for low dimensional varieties. If it is of general type, well, intuitively it is something like hypersurface defined by inequations of a high degree, and then you will find no rational curve of it on it, and no chains of rational curves and so on. In the moduli space there are lots of rational subspaces. However, it in a whole it behaves like manifold of general type. So this is one of the reasons why perhaps the more abstract point of view, when we do not consider M sub j as a manifold, but try to understand it in a from a wider point of view, is quite natural. And well, in terms of this course, this is, as I said, one of the two motivations of considering Grotendika topologies together with the attack cohomology. Okay, so today we'll discuss both objects. Again, the fine modular spaces will be discussed in a bit preliminary form. So, as I have defined it, maybe several times before today, the easiest thing is to define the modular space occurs set theoretically. Sorry, we have spent some time to develop not a quite standard formalism. So it is the catalog of the subcategory of standard algebra geometric categories that of curves. So there are curves over the field Okay, and we need nothing more. I just remind that whenever we have a category, here it is the complete category of curves. Of genus J. The curves up to isomorphism. By the curves here and during the whole lecture, we mean complete, irreducible, simple, and non-singular. So it is a set, or this set with every fixed J, and as I said several times before, it is not at all easy to give it an appropriate structure. So let me spend some time to give it a structure that is by no means final one, but that moves us towards algebraic geometry. So the structure of I'll use the word orbifold, fold, meaning locally and vector. Since it is real, it is a purely transcendental definition vector of, say, a ball over finite group. So this structure is easy to define, but it is, it gives what was really considered over complex numbers, and it is quite a transcendental object, though related to the algebraic one. So now let's recall that for x such a curve in our sense, so then it's with the fixed points, then the fundamental group. Well, in most cases people skip such things as the marked points, but in the Grotendika topology theory it is a very important point, and I should say that though, it is closely related to the question about the universal cover, that though seemingly it is a purely Archimedean concept, or the concept over real numbers, it really works in a much more abstract setting. And then it is defined with the canonical generators related just by one long word. So it is one. So this is an abstract group generated by the loops centered in the marked points, and there is a real manifold, the set of representations of this group in SA2 of R. So perhaps we denote it just by the, well, maybe some J. So what it is, equal to the subset of SA2 to R to the degree yes, all of them. I should write P here. All of them are matrices depending on three parameters. So they are the tuples of 6J, to the 6J, and this is there are three relations. This one is a relation in PSL. Therefore, it gives three relations. Well, here I mean that we realize X as an X tilde is universal cover. That is the upper half space over Y1. And the general theory of uniformization says that such a representation is defined up to the common conjugation that gives again three, diminishes this dimension again by 3 dimensions. What is really, and this is quite a real algebraic variety, a very important one and very interesting one, and studied a lot during the recent decades. Of course, it was studied over arbitrary fields, not only the real ones. But this is a terribly transcendental relation, saying that the group generated by all these generated by these elements is discrete. And of course, you cannot formulate it in the algebraic language. So this realization of the modular space gives us something. Tells us that the ends of J of C, here we mean that J is strictly larger than 1. The cases of small j's should be treated separately. So mj of C, its dimension, so it is, as an object, it is it was written already that it is a real orbifold. So because this group acts with finite stationary groups corresponding to the curves with non-trivial automorphisms. So it is a transcendental singular object. However, we can calculate its dimension, and it is 6j minus 3 here, minus 3 here, so it is 6j minus j, and this is what was known to Riemann, well, with another argument, the argument that I do not reproduce here. Riemann was considering curves over together with their columns over the projective lines, and it also allows to count well. In 19th century it was quite a non-trivial matter to understand that this covering is defined by the singular points and the discrete invariants, the monodromy groups. All of this was guessed by Riemann and made mathematically precise by other people, mostly Hurwitz. And this argument was performed over C, and can be literally transformed to other manifolds, over other ground fields. However, for almost a century, this object was considered as an intuitive one, and the precise definition, though based on quite a classical discipline, geometric invariant theory, was gave a precise algebra geometric definition only in 1960s, again mostly by Mumford. So this is a sketch of a long story towards the understanding of moduli spaces in the set theoretical frame. Now let's look at this object from the point of view developed in the previous lectures. So, any questions about this? So this is a very, very short overview of the moduli space of, well, I don't, it was an arrow, we should keep this in mind. So for the time being, I give no argument for the reason to consider the prime moduli space. And we return, I restore the notations of the previous lecture, and sorry again for, well, three kinds of B. Well, bases, so we used some calligraphic one, then category of bases that contains the object of these categories are bold-faced. These also called just bases that contain the points B. So this category is some category of schemes over K that is going to be fixed, and we considered families of curves that are X calligraphic P over the bases. Yes, I'll put here that technically it is enough for today to consider the quasi-projective variables. Though, as I said before, I do not fix this category, since in some vertices it is profitable to consider non-reduced schemes with a nilpotence in the structure sheaf, which is quite convenient to consider infinitesimal deformations. So the families are like this with X sub B's. So sorry, I should write these letters in a very distinguishable way. B sub B will always mean the scheme image of B, the scheme 1. That means that when this should be considered geometrically and will be generalized. I'm giving the scheme theoretical details here because well, the Grothendika like constructions in this part of mathematics are very important and very non-classical. So here we have one point variety, just one point, and when we put it here, map it to the base here, this object, sorry, well, I'll write it like this, x sub b is nothing but the product of the whole x over, so it is mapped to the base B as well as the spectrum of the field does. And here is so this B is just a point. So the condition that all these fibers are curves of genus G. Here I just repeat the end of the previous lecture, and now we consider the functor of families. What is it? Families indexed by J is a functor from the category B to the category of sets. That associates to every object B, that to every base B. Here we can use the developed notation, the catalog of families. Well, let's write it once. Families of genus J. How do we write it? Just write it in a word. Over B bold. Of course, we are considering the category, and it is very important intuitively. I'll try to find the appropriate place on the blackboard. So, given B, B is bold now, not its picture. Being B, we should think about families like this, and of course the morphisms for families are just the algebra geometric morphism with such a diagram, isomorphic, such a diagram being commutative. So, as usually, we have the essentially small category over B. Well, maybe one should spend a minute to understand why the category of families of curves over given B is essentially small. The easiest way is just to reformulate it in terms of field extensions. Anyhow, it is, and so this association is is very well defined. Now, of course, as usually when we have a functor with a set valued functor, we have the central issue about this functor. Is it representable? Now I meet a traditional pedagogical difficulty telling about this material because what is really easy is to tell about the dream of such a representability. So I'll use a trick and we'll see that literally, really, and unfortunately, madly, no. And one could consider it as a negative result in mathematics. Very soon I'll give a very simple explanation, but the difficulty I mentioned before is just telling about explanation about why we dream about its about the representability of the functor of the families. So I think all the actors are defined in a rather memorizable way. Any questions about what is written now on the blackboard?
So if we consider maybe some other type of functor, which maps B to isomorphism classes of curves.
That is to moduli spaces.
No, maybe another functor may be defined as B goes to the set of isomorphism classes of curves over the function field of B. And it is almost families, maybe in some birational sense. I just wanted to ask.
Do you mean that there could be an alternative construction over the function fields? Well, the thing is in these constructions, just of course any family of curves can be considered as one curve over the field of rational function on the base.
Yeah.
But it is terribly, but the field of rational functions of the base, which is different from the point, is terribly algebraically non-closed. The approach is quite correct because, well, as soon as we work, we meet an algebraically non-closed fields. We consider all its algebraic equations, and all of them constitute, in fact, very nice and important Grothendieck topology. And maybe when you were asking about universal covering, you meant something like considering all the algebraic extensions together. Algebraically, it just means to change rational functions on B over its algebraic closure. But this object is quite non-constructive. Though very important from theoretical point of view. What we are discussing now is much closer to the finite dimensional algebraic geometry over the base.
Okay.
But the direction is the directional thought is quite correct. So I erase almost everything, but these names well, and perhaps I can give more precise sense to these two notations and words. So the functor of families is not, well, I'll explain in a while why it would be natural to dream about it being represented by the coarse moduli spaces, but is not, and it is really represented by fine moduli spaces, but in larger categories. So I would say a dream, or well, perhaps the representability dream. I have at every step I have to choose between two objects. So first I give a notation to the object that really exists. So for every family, or a family X over B, we have the mapping of the let's stress that it is a set morphism B to M sub G of K is defined that associates to B the class, yes, we can use this notation X sub B in, yes, for the time being, J of A is just a set of classes of equivalence, and by the square brackets we denote choosing the class of equivalence. It is really defined, and if we had the verb if the universal family existed, I would write a bit later That means here we imagine the moduli spaces as it is, and over every point of it that is an equivalence, an isomorphic class of some curve, we would find a curve, this very curve. If we were able to collect all of them, all of the curves of G and G into one universal family, then the family functor would be representable by MJ. Let me draw it again. So, well, some sentences is complete. The set morphism, like this. Well, sorry. If yes, the universal family existed, then the family functor G would be representable just by M G of K, just in the most, I think, in a rather obvious way. So it is drawn here. Now suppose we have a family here, be bold, just draw it now. We did not give it a name, so this depends on the family X. Sorry, there is no standard, as far as I know, there is no standard name for it, so this is well, it is the classifying map. It is the classifying map. So let's denote it by classifying by X. So for every family X, we would have a classifying map, and then we would have here, we have the classifying map from any, for the base of any family, and then the whole set of families sub J of B would be in one-to-one correspondence of the morphisms. Here we use here we call our category of bases, and we consider the morphisms in this category from B to MG of A, because the family would be restored as base change of so we have this would be universal J with that considered pi G. What is really difficult is to speak to discuss the non-existent objects. What we discuss now does not exist literally. It exists in some, well, it exists after certain variations. And moving to fine moduli spaces into Grodenic topology is one of the possible variations. So if we had this, then it would be just the fiber product of B over mg over k by uj over k, because over every point here we would just pull back the corresponding fiber of the universal family. This would be another simpler world in which we do not need any Grodenic topology. But we happen to live in another world. So this wild, so I was speaking about the representability dream. Now it is written down on the blackboard. Good. So now, why literally it is but a dream? Can I erase everything? Sure. Any questions?
I have one question. Do you understand correctly that this requirement about the existence of the universal family?
About, sorry, what?
About the existence of the universal family, it is more strong than the requirement of representability of the factors.
Yes, it's more strong. It would be.
Yeah.
However, this yes, this is correct. So now, why, in fact, the Panther family is non-representable? Well, sorry, maybe I change the order of this lecture because we are closer to the question of what a course moduli is, and discuss briefly the structures on the course moduli spaces. It is a funny story, but really we should always mean it. Considering the fine moduli space. Suppose we have a set, but for any, let's duplicate the quantifier for any b, any base, bold base from our category we have a set of bases. That's 2 and G of K. Now I'm writing this in these marks, saying that it is in some sense covered covering by all B. That means that just foundationally we have a set and lots of objects from the category with the concept of regular mappings here, regular set theoretical mappings. I should confess that I don't know the corresponding precise algebraic theorem that would tell us that under such and such condition there is the only structure on MG as an object, say, of the category of the projective manifold, such that all these morphisms are all these set theoretical mappings are morphisms of the category. However, they are, and what is immediately obvious that the family of such images really cover the moduli space. Any point is included at least in the constant family, but this is a true problem in algebraic geometry. What kind of families of curves do we have? Or in other words, if we take a curve here, a point here, just in a set here, what are the classes of family of curves containing it as a fiber? Infinitesimally, it is just a theory of deformations of curves. Well, and I have no time to discuss other structures on MG that were developed in complicated transcendental theory. The topology was defined, a very special metric, and so on. However, we stick to the methods of this course. But I'd like to emphasize that for the time being, the course moduli space is defined as a set with lots of algebra geometric morphisms to it. Okay, so I erase it and explain the non-representability even of the simplest one. Just by an example. So consider the curve x pointed sub t, sub epsilon perhaps, epsilon defined by expression y square is x cubed minus epsilon. So here just b, this base here, the base here, no, sorry, the base here is just the affine. Let's write it down like this, just k dot. That is epsilon is supposed to be any non-zero number, and this is a family of curves of genus 1, epsilon over 0. It has singularity, otherwise it is a family of genus 1 curves. Here is my attempt to draw it. And the point here is that, well, we were initially we were going to consider the complete curves. These ones are affine ones, but let's decide that we are just lazy to write its equation in the projected coordinates. So this family is isotrivial. That means that it becomes trivial under the base change. So here it is defined over the epsilon line. If we could extract the cubic root over from epsilon, it would become really trivial. So here we have well, epsilon being, let's consider here delta and delta 2. Delta cube here, and here it would be trivial. All these curves would become isomorphic just by the obvious change of coordinates. We would transform them to the trivial family. So here it is isomorphic to, well, y prime square equals x prime cube minus 1. Just good. Is it really correct? Or do we need, perhaps we need the 6 degrees, yes, 6 degree, so that we could relate y prime also to 1 in an obvious way. So this is such a special phenomenon that after the base change, the family becomes trivial, but itself, without base change, it is not trivial. Now, of course, we should discuss the arguments why, and I should say that it is a good point to apply the Lefschetz principle, at least for zero characteristic, because this non-triviality is so non-trivial family is non-trivial over C, and we immediately understand it by the topological considerations, by the monotony, as soon as we, as soon as we go around the point corresponding to the singular fiber, our transformations of homology become non-trivial. Only after going around the special point 3 times, we make it trivial. As for the other fields, we could either develop the arguments like Lefschetz principle, what is proved by transcendent argument is generally true, or develop some kind of the abstract cohomology theory that also can be done and will be outlined in this course in terms of étale cohomology, so that the monodromy is well defined, and we have the argument about non-triviality of this family over arbitrary ground field. Now this example breaks completely all the hopes for the representability, because since over some larger base the family becomes trivial, all the fibers are isomorphic, which is of course obvious without any abstract algebraic geometry. Therefore, as soon as we have our M1, and then we have classifying, and maybe we have denoted by classifying X, is just constant. Its value is just constant, and well, we know perfectly that it is the modular space 1. Seems to be, well, this is really a coarse M1. Well, we can loosely formulate it that it is just a G line. So the value of classifying map is constant here. So though in some sense we almost have the feminism here, we'll discuss it. We have problems here, and we have problems in another radio. Well, cube here. Again, we have problems. Otherwise, we have a perfect universal family. So it is spoiled, in fact, only by the examples like this. So the reason of not working, non-representability is, it is clear by this example that it is somehow related with the rare curves having extra symmetries. So one of the ways to overcome this problem is, besides getting rid of all the curves with symmetries, and by the way, with non-trivial automorphisms, by the way, as soon as J grows, the codimension of the curves with automorphisms becomes smaller, becomes larger and larger. So these are parts of the moduli space that are quite negligible. However, we'd like to have an ideal object. So the dream, the naive dream of the representability is broken by this example. However, what was said today about the Grothendieck topology perhaps shows how to overcome this problem. Just, well, having in mind exactly this example. It means that it is insufficient to consider just families in the classical sense, and to consider just MJ it is. If we consider families together with all the base changes, together with all the coverings, it would be an excellent object example of Grothendieck topology. And then our what will come in place of the coarse moduli space will be the fine moduli space, and the functor family will be very well representable. So this is the general direction, and our time is over. Any questions, please?
So I think this argument does not work in the other direction, right? I mean, if a family of curves is topologically trivial, it does not necessarily trivialize on the risky.
Yes, it is true by the purely topological origins. Since it is, I think, the stronger statement is true. That is, if the classifying mapping induces the trivial morphisms of fundamental groups, it is constant.
But for me, it is strange because it seems there are quite a lot of families of elliptic curves over pi1, for example, but I don't think that there are a lot of vibrations of pi1 into tori.
Sorry, I don't think I follow you. Maybe you write down what you mean still in the frame of the lecture.
I think it is not very important, maybe.
It sounds like it is, but maybe we discuss it further in detail during the next lecture. Okay.